Hello, welcome to the Open University on BBC One. Today our lineup includes an important development in immunology, an undersea gas pipeline and the Hindu caste system. But we begin with the course on engineering mechanics. It considers two systems, a centrifugal fairground ride and an internal combustion engine, and it performs a dynamic analysis on them using the procedure outlined in Block 4 of your text.
We looked at this engine in the first television programme, when we used it as an example of a slider crank mechanism. Then we were interested only in its geometry, the way in which the translation of the piston is converted to rotation at the crank. In this programme, we are going to look at a dynamic analysis. I'm going to estimate the force which acts on the piston at top dead centre. This is the point in the engine cycle when the acceleration of the piston is greatest. You should by now be pretty familiar with the line diagram of a slider crank mechanism. Now we're going to look at the actual components which make up that mechanism in the engine. Here I've got the crank, that's the crankshaft. And here the piston and the connecting rod. The connecting rod, the piston, and the pin joint is made up by a component that we know as the gudgeon pin. So, these are the bits which go up to make the heart of this engine. And it actually works on a cycle we know as the four-stroke cycle. And to give you some idea of what that means, I've got a cutaway model. Here we have the piston, the connecting rod, and the crankshaft. And through here, the gudgeon pin. Now the four-stroke cycle means that the piston actually makes four movements during the cycle. The first, it moves down the cylinder, the inlet valve opens, and the petrol-air mixture is drawn in. On the second stroke of the piston, this petrol-air mixture is compressed. That's the compression stroke. And on the third stroke, the piston is actually forced down the cylinder by the gases which have been ignited by the sparking plug and are now expanding down this space. On the fourth stroke of the piston, it comes back up, forcing the spent gases through the open exhaust valve and out eventually into atmosphere. And it's at this point that we are actually going to do our dynamic analysis. Well, if you're not familiar with a four-stroke cycle, that may all have seemed a bit complicated. Certainly I went through it quite quickly. I don't want you to worry too much about it. What I do want you to grasp, though, is that at this point in the cycle, there is virtually no difference in the pressure on the top of the piston to that of the atmosphere. So we have no significant pressure forces acting on the piston. And that's why I chose to do the analysis at that point, because I'm really only interested in the forces which are required to accelerate the mass of the piston. Well, that's, in outline, one of the problems which we're going to analyse in this programme. And we're going to do it using the procedure which you saw in the text. Now we're also going to look at one other problem. Well, if you've ever taken a ride on one of those fairground machines yourself, you'll know that it can take something of an act of faith to actually get in and trust that you won't fall out when you reach the top. And rather than try it out for myself on the real thing, I'm going to use this model with a non-breakable human, which I can place in the cage and do an experiment to find out the conditions of safe operation for a device of this kind. I'm also going to check the experiment on the model with a dynamic analysis, which will predict the safe speed for rotating this wheel so that the man inside won't fall out. Well, those are the two problems we're going to look at: the dynamic analysis of a piston in an engine and of a man in a fairground machine. But before we start, let's just remind ourselves of the basic law of mechanics which we're going to use, Newton's second law of motion, which relates the acceleration produced by a force acting on a mass. If a mass is acted on by an unbalanced force, then it accelerates in the direction of the force. The acceleration A is proportional to the force R and inversely proportional to the mass m. In the SI system of units, if a mass of 1 kilogram is acted on by a force of 1 Newton, the resulting acceleration has a magnitude of 1 meter per second per second. Let's take a look at that. The acceleration is inversely proportional to mass. So, if we double the mass, the resulting acceleration is halved. Alternatively, doubling the force will result in the acceleration being doubled. Remember, both force and acceleration are vectors. Both direction and magnitude are important. So if the direction of the applied force changes, the magnitude of the acceleration doesn't change, but the direction must be in the direction of the force. When solving problems, it is often much more convenient to work in terms of the rectangular components of the force and acceleration vectors. And if we follow the x and y components of the force, Rx and Ry, we can see that the resultant acceleration A is the vector sum of the component accelerations AX and AY. Well, we're now ready to apply Newton's second law to the dynamic analysis of the two problems we started out with. And we're going to proceed by working through the series of steps which you've already practiced in the text so far. Step 1, assembling the relevant information. Step 2, drawing the free body diagram to identify the important forces involved. Step 3, applying Newton's second law in the form R equals ma, where R is the resultant force acting on the body, m is the mass of the body, and a is the acceleration of the center of mass of the body. Step 4, deciding on the kinematic constraints, which give the form of the acceleration deduced from kinematic relationships. And step 5, elaborating the forces which were identified in the free body diagram. And by combining the equations from all these steps together, we end up with the equation of motion for the particular situation we're interested in. Then it's just a matter of substituting in the given data and completing the calculation. And I hope that you've found that this procedure has already been useful to you when you've been solving dynamics problems yourselves, even in situations like our two problems, which at first sight seem quite different in character. So, without more ado, let's get back to Dudley working through the procedure with his engine.
Well, step 1 involves assembling the information which I'm going to need to perform the analysis. Remember that we're trying to calculate the forces which must be applied to the mass of the piston to accelerate it down the cylinder. So the first thing I'm going to need is the mass of the piston. That's 220 grams, which is, in SI units,
0.22 kilograms. Now, to get any information on the acceleration of the piston, I'm going to have to do a kinematic analysis. So I'm going to need some data regarding the geometry of the mechanism. I'm going to need the length of the conrod, I'm going to need the crank length, and I'm going to need the speed of rotation of the engine. I'll start with the conrod length.
That's 108 revolutions per minute. Well, my model appears to be working successfully now. At least the man inside hasn't fallen out yet. Now let's see if we can analyze the situation theoretically. Well, I've gathered my information. The radius of the drum, R, is 0.02 meters. And the mass of the little man inside is 0.02 kilograms. And I've just determined that a safe operating speed for this drum is 108 revolutions per minute. And I'll just convert that to consistent units. That's 108 multiplied by 2 pi to get it into radians, divided by 60, get into seconds, and that comes to 11.3 radians per second.
Well, I think that I've got all the data that I need. We've got the mass of the piston, that's 0.22 kilograms. Connecting rod length is 0.1 meters, crank length 0.03 meters. The engine speed, well, I've taken the maximum speed of the engine, which is 3,600 RPM. And to do the calculation, I'm going to need that in radians per second. So that's RPM times 2 pi gives me radians per minute divided by 60, 377 radians per second. Step 2 involves the free body diagram. What I've got to do here is isolate the piston from its environment just to leave the forces which are acting upon it. So here we've got the diagram. The first force, well, that's the weight force, W. And C, well, that's the force that we're looking for. That's the force from the conrod and gudgeon pin accelerating the piston down the cylinder. Would you expect there to be any other forces present? What we do is we have to look around the piston to see where it is in contact with its environment. Obviously, it's touching the cylinder walls on the side. We would expect there to be a friction force, which there will be. But since it's a lubricated contact, I'm going to assume that I can neglect those friction forces without affecting the analysis. Similarly, there'll be a pressure force on the top of the piston. But as we discussed earlier, on the exhaust stroke, those aren't going to be large enough to be significant. So the only forces on my free body diagram are C and W. And there's one other thing which I've got to put on any free body diagram, and that's the coordinate system which I'm going to work in. I've chosen XY coordinates, and I've aligned the y-axis with the forces C and W and the consequent acceleration of the piston. And really, that's the crux of the problem. From now on, it should be downhill.
Well, let's proceed. Remember, what we're interested in is the limiting safe condition for the man to take a ride on the wheel. And the worst possible situation would be when the wheel itself was right up in a vertical position and the man was at the top of his travel. Now let's consider what the forces are which are acting on that man in that position. The free body diagram will identify these for us. Well, I've chosen normal and tangential coordinate axes because I'm dealing with a rotating situation, and I'm interested in the forces acting normally towards the center of rotation and tangentially in the direction of travel. And there are really only two forces which are of interest to us: the weight force, W, and the force P, which is acting on the man's back from the cage wall. And this will be, again, normally towards the center of rotation. Of course, you might expect that there would also be a tangential friction force acting between the man's back and the cage wall in the tangential direction. But remember that the man and the wheel are both turning at a constant angular velocity. And this means that the tangential acceleration is zero, so that the resultant tangential force will also be zero. So we're left with just two forces, P and W, both acting normally in a positive direction.
I want you to keep in mind the free body diagram. Well, the two forces, C and W, both positive in the direction of Y. When I come to step 3, Ry must equal C plus W, and that must equal the mass of the piston times the acceleration in the Y direction. Step 4, kinematic constraints on the motion of the piston. That turns out that the acceleration in the Y direction at that point in the cycle is r omega squared L plus R over L. And that won't be familiar to you, but it's a formula which can be quite easily derived from the kinematics, and in fact we've done that for you in the program notes. Step 5, looking again at the forces. Well, W equals mg, well that's pretty familiar. C, well we don't know any more about C, that's exactly what we're trying to evaluate. But with these equations which we've got in the 5 steps, and the data which we took in step 1, we should now be able to evaluate C. Here we have the equation which we generated in step 3. C plus W, which equals mg, equals the mass of the piston times the acceleration, r omega squared L plus R over L. And if I rearrange this equation in terms of C, which is what we're looking for, I get this line here. And now I can start to put in the data. M, well that's 0.22 kilograms. R is 0.03. L plus R must be 0.13. Over L is 0.1 minus G, 9.81. And now I can evaluate it. Right. Before we continue with the evaluation, there's something which I'd like you to look at. Look at the relative magnitudes of these two accelerations. In fact, the contribution of the weight force is virtually negligible. 9.81 is about a 500th of the acceleration due to the actual kinematics of the mechanism. So in fact, back at the free body diagram stage, I could quite well have neglected the weight force and only included C. If I go on to evaluate, finally, it turns out that C equals 1.22 kilonewtons. So the force from the conrod on the piston to accelerate it is about 500 times the weight of the piston itself. So I hope you can see that as far as an engine designer is concerned, those sort of forces are very important. And in fact, this is quite a low-revving engine. If you are designing a racing car engine, you might be working at 12,000, 14,000 RPM. And those forces become very important indeed. Well, with the help of our procedure, we've managed to do our analysis of the piston. I wonder how Tony's getting on with his analysis of the roundabout.
Well, with the free body diagram for my man at the top of his wheel complete, I can now move on to step 3. The resultant force acting on the man will be in the normal direction, Rn, and will consist of the sum of the two forces, P on his back and W his weight. And by Newton's law, this must equal his mass times his acceleration, again in the normal direction, AN. But what is this normal acceleration that he experiences? Well, we know that a point moving on a circular path will experience a normal acceleration towards the center of rotation, and that normal acceleration, or centripetal acceleration, is given by the product of the distance to the center of rotation and the square of the angular velocity, r omega squared. We can now go on to look at the individual forces, P and W. Now remember that P is the force on the man's back from the cage wall. And in the experiment I did earlier, I know that at a high enough speed, I can operate the wheel safely. He stays on the wheel. But if I operate it at just enough speed so that when he gets to the top of the wheel, he's just falling off, and I know that that's my limiting safety condition. That is the minimum speed for safety. And at that condition, he won't be feeling any force on his back because he'll just be leaving the wheel. So P will be 0 at the minimum angular speed. The other force, W, of course, is just his mass times his gravitational acceleration. So, now let's put all that together. Here is Newton's law. The resultant force acting at the limiting condition is just his weight, mg, since P is 0. And that must be equal to his mass times his normal acceleration, which will be r omega squared minimum. And it's interesting to note that the mass of the man cancels out on both sides of the equation. And that's an interesting point because it means that the safety criterion will not depend on the mass of the individuals who get onto the wheel. And we'll test that proposition later. So with the mass cancelled, we get omega squared min is equal to g over r, or the minimum speed is the square root of g over r. We can calculate that. Square root 9.81 gravitational acceleration divided by 0.2 radius of the wheel, square root, and that comes to almost exactly 7 radians per second, or 7 times 60 divided by 2 pi, which equals 67 revolutions per minute. And that is the safe operating speed for this wheel. And that confirms my earlier experiment when I was running at 108 RPM that it was safely operating. Well, let's just check that analysis with one more test on the model. Well, here's my man. I'm going to put him in his cage, run the model up to speed, and then slowly reduce the speed until he just about falls off. And we'll check that speed. I'm also going to use a little man with less mass just to check the proposition that they should both fall off at the same speed, irrespective of the mass. Right. Now I'll slowly reduce the speed. There goes the man and the boy, and that was at a speed which agrees quite well with the results of our dynamic analysis.